Yep, let's start where we ended yesterday. So we were starting on predictor-corrector methods, and I'll repeat the definition. So the definition of a predictor-corrector method is that the explicit method, or you use an explicit method to predict an approximation. Predicts an approximation and then you use an implicit method to correct this prediction. The or an implicit. Prediction. So an example of this could be that you're trying to solve, for instance, y differentiated equals e to the power of y. This one you can't, I guess maybe you can solve it analytically, but if you try to use an implicit method, you can't make this implicit method explicit. That's why you first have to use a intrinsic explicit method, meaning that it's explicit just from the get-go, and then use the implicit method with your approximated guess. So for instance, you can use Adams-Bashford. Let's see, I think this is 3-step Adams-Bashford. So I'm just writing these on a blackboard, so you can use 4, if I 9. Last lecture we figured out how to actually create these. Minus 9f I minus 3. Okay, so is this an explicit method or is it an implicit method? Any guesses? No? So it's a okay, so first a guess. Who thinks this is an explicit method? Okay, yeah, and who thinks it's an implicit? That's good. It's an explicit method, and why is it explicit? You see this first here? Fi. So you only have the plus ones, the ones you want to try to solve on the left-hand side. That's why it's explicit. Because you can explicitly express this. And an implicit method like this, and here you use forward differentiators to figure out all of these constants. I 5 minus 2 plus f minus 1 I minus 2. Okay, so why is this an implicit method? Oops. Because you have this plus 1. It could be possible that you can actually solve this function f here, and you will be able to express this in an explicit manner. And that's why I try to introduce the notion of an intrinsic explicit, because then you don't have to do anything algebraically in order to try to make it explicit. So first, you do, I can maybe also list what these are. So these are the 3-step Adams-Bashford. So Adams-Bashford. This is the 3-step Adams-Moulton AM. So Adams has been doing both of them. I mean, the names aren't really that important. Just if you want to find the methods again, then you can Google them. So, step is here. Step 1. Okay, so you remember what I said about starting values? So if you're only given a value for y0, in order to actually use these two methods, multi-step methods, you need to estimate more points to use. So you could use single step, or you could do more advanced then. I mean, first you have to use a single step, but when you have 2 points, you could use a 2-step process. Compute, so I assume you're given y0, so then it's y1, y2, and y3. Yes, then you should have everything you need. Step 2. Use B, so the top one, to find the next one. Y4, and then tilde, and next, you correct it. To improve or correct. For get y4 without anything. And then you increment and you repeat these two in order to solve it. I mean, you could also try to insert this method. In essence, you could just make one big method. But it's easier to think about, first I do this and then I do this. Okay, but you also saw that the ODE 4.5, in MATLAB, we had a variable step size. How do we determine this? Try to take a look at all the tricks. Step size. And you read that. Okay, complete. Okay, so for these two methods, it's going to be a final example. We have that the Adams-Bashford error to be 1 minus the guess. So the difference here is that this is the actual value, this is the guessed or approximated value, the predicted value. So sorry for not taking fails. 5 times differentiated, and you have this yi. And it's molten, again, y of ti plus 1. This is exact. This is the corrected value here, yi plus 1. For h. So this is the error in the Adams-Bashford, the first one, and the Adams-Moulton 3-step methods. For 720 and this could be a different so I also see that in absolute value, the error of the implicit method is lower than the implicit method. In measure. Okay, but we will assume, in order to do something like this, we will assume these two approximately. Okay. What we want to do is try to clear errors. Okay, so looking at these, here as we have, oops, 1, so the corrected value minus the approximated value or the predicted value. So this is corrected. From the implicit equation, and the other one here is the approximated one from the explicit. Okay, then we can actually look at the difference in this. So just plus 1 h, that's from over here. 4 over 720 1 5 19 of that's from over there. Mu hat, mu I hat. But we assume that these were equal, so we can just add them. Meaning that we get approximately 3 eighths for y I with hat. Or the term here, y differentiated approximately equal to 8 over 3 h fifth plus of h over there of yi 1 yi approximated. Okay, and then we have our yes. So did you come in? Okay, no. So first we finished the predictor-corrector methods. That was just a recap almost with an example. So use an predict with an explicit method, correct with a implicit method, and now it's variable step size, as you saw with the OD45 MATLAB. It changed the step length. So here we're looking at the example more closely. So this is from the error of the Adams-Bashford and Adams-Moulton, and then we'll look at the error and how that actually behaves as a function, and we can actually use this to predict or estimate a better step length. But I also give some rules, because if we just get a better or worse error, you need to do a lot of extra function evaluations. So if you have a very, very tiny intervals, of course it will be better, but it might not be worth it. You might want intervals like this. So you have to fine-tune this depending on the error you're interested in, or your error tolerances. That's what we're trying to do in the end. But there's some back and forth first. So we can use this to look at the truncation error. Was that okay? Yeah. Y of t. Again, this is the exact value. The difference between them, always positive, almost 7, 3, 8, 4. So this is from the error of this over here. So we try to estimate this bit. So that's why I have 19 over there. And then we have this y 5 times differentiated. That's what we try to approximate over there. That was 8 over 3. Five y of I plus 1 minus 1. So only thing here we can actually use is the how much we predict, the measure of how much we No, sorry, how much we correct the prediction. So yeah. Yes, when we've done both of them. So when we've done the approximation and predicted it, then we get this truncation error. And here we see this is the corrected prediction, and this is the prediction. And this one over here, that's the exact value, which we don't know. Yeah? They look similar, but then I don't have to introduce a lot of different variables. And they are very related. That's why the prediction, correction, and the absolute correct one, we don't know. So approximately equal. Okay. 19, 270. And that is similar to the OD45, only that uses both RK4 and RK5 and looks at the difference. This, yes. 20 and 20. Ah, no. Of course, that shouldn't be. Oh, yeah, no. I assume if you do this calculation, then you will get this. Yeah, no, yeah, it looked like I had switched them. Okay, so if we try to reconsider the new step size, we also get new approximations. So we want to choose, write this one, 270H, 270. Okay, so now we can actually use this to try to figure out if we want to increase or decrease the step length or step size, as I've written earlier here. So what we want to do is we want to choose Q, kind of a scale. A real number. Yes, such that truncation error that's the TI is bounded by some kind of number. So we have to also pick how accurate we want to be. And if you want to be very accurate, well, you still have an error in the roundoff in the computer. So that's kind of your low limit of this epsilon. What we want to do is TI H I'm going to call this a hat because here we are trying with a new step size. So this is the corrected result with a new step size. Now we have a hat. So step length, step size. QH. Over QH. And Q could be either, well, 2 or a half, a fourth, 4, 0.3, depending on how you set the algorithm. 19 over 720 Q to the power of 4 times H to the power of 4, plus we just switched Q with, no, H with Q times H. 5, some kind of mu. There we go. 19 for H. 20. Five. Minus y I plus 1 tilde. Like so. And there you see this is from the previous points. Okay, so let's just continue this line over here. Get right again. Y T I plus UH. This is the correct value, but we don't know what it is. It's I believe no. QH. And this is our truncation error that we want to be less than some kind of set value. So this should be less than. Okay. No, sorry, I forgot. Q4 over there. And then we can solve this equation here for Q. So should we get a bound for Q? To 17. The difference in the approximated or predicted and corrected values. Fourth. This should be approximately 2 plus 1. 1/4. Okay, that's just a number. The thing is here that we've also done a lot of pessimistic approximations. So this 2 here, this is kind of like an upper bound, we could say. So in most practical applications, this factor here, this 2, it can be lower, because we've been too pessimistic. So this is just somebody has try to implement this algorithm, they've looked at it, they've tested it, they've tried it, and they see that this 2 times this, that's too pessimistic. It's way too pessimistic. Oh, not way too, but it's a bit too pessimistic. So they've figured out that in my algorithm, if I just change this 2 to 1.5, I get better results. So it sounds like kind of hocus pocus. It's more like engineering. You try a lot of stuff, you have some math behind you, but then you see that maybe I've been too pessimistic here, or maybe I've been too optimistic, so you have to do something in between, oftentimes. Find. So also when you program yourselves, for instance, the project, it will be kind of open-ended. You can do a lot of stuff in the project, but don't do too much in the project. So I'm trying to create a, well, can you actually just say it? The project is going to be based around full waveform inversion. So you will do simulation of waves, and you will also try to update the model of the gradient. And then I will tell you how you create this gradient, but you have to implement the wave equation, acoustic, just simple one, and also a gradient update routine themselves. It's not going to be too complex, and I'm available on Slack when you do it. And there you might want to do stuff like this, just like, I see that it works better if I do this, then just do it. So we're going to say that QS approximately equal to 1.5 E and then 1/4. I will also in the project going to give you a framework, but you're free to change the framework. There are some variables that should be set different types, and then I hope I don't have too big of a model. We'll see. Anyway, what we want to do then is that if epsilon is between, so this epsilon we picked, if this is between the truncation error is going to be, no, it's way behind us. The truncation error is this bit, almost. Yeah, so this is the truncation error. If this is between epsilon divided by 10 and epsilon errors, then we want to change something with step length. If this, yeah. Oh, this is something you've picked yourself. The truncation error is something that's built, or not built into, but it's what you get out from the system you picked. So this epsilon, that's kind of the acceptable error. You set it arbitrarily. So you say, I want to be this and this accurate in my simulation or calculation. But you have a lower limit on it, and that's the machine precision. It can be actually very low, depending on if you use floats or double precision numbers. But usually it's around 10 to the power of -6, again, depending on the problem. So this is just something you have to pick. But if you see that your truncation error is more than your acceptable epsilon, then you have to have a smaller gap. Then you can set, for instance, Q equals a half, and you update your H to be 1/. So basically, you half your intervals. I mean, you could also have a thrice, but halving and doubling, that's usually what's being done. think so. Yeah. And if it's less than yeah, your error divided by 10, then you can actually increase your intervals. Then you set u to 2, and your new interval is just 2h, meaning that you are inside acceptable levels, and you can increase your step size. So you need fewer iterations, or not fewer iterations, but fewer calculations at least. Yep. And the reason why you have this big of a gap between them is that when you actually make changes to your step length, then you need to do all the calculations, or not all the calculations, but all calculations in this step you are in again. So you don't want to be changing your interval too much. You want it to stay put. Okay, so that was all for ordinary differential equations, and we'll start with PDEs. Unless there are questions. No. So then before the break, I will give a very general introduction to what a PDE is, or partial differential equation. For instance, heat transfer is a PDE, or the wave equation. Again, numerical solution of these. Or DE. So the general form of a second order partial differential equation is PDE. A times UXX or UXY, UY, D, X, and this is a variable, not differentiate. E, U, Y plus F, U equals some kind of function G of X, Y. And this G of X, Y can also have constants in it. So have you seen this way of writing differentiation before? Okay. And like a quick side note. So UXX is the same as the squared U, the same as the x squared U. Same with UXY, dx, dy, U equals d dx dy. You can see why I prefer it this way. That's the right. But this means this. And by looking at the A, B, and C, we can say if it's an elliptic, parabolic, or hyperbolic PDE. Where I'll stop. I'll give some examples maybe also. So we can look at B, minus 4. C, first we'll look at elliptic ones. You see, this is less than 0. Have an elliptic. If it's equal to 0, we have a parabolic. And if it's less than 0, have an hyperbolic. Hyperbolic PDE. And why these names? Well, if you try to look at the plane in this case, this will kind of trace out an elliptic curve if A, B, and C. Oh, well, if this holds true, then this will trace out either an elliptic curve, a parabolic curve, or a hyperbolic curve. And all of them have slightly different characteristics. What are examples of these? Well, seen some of the examples before. For instance, an elliptic. The ones they are x plus y equals 0. That's the Laplace equation. X y equals to some kind of in here. Y also for fish, I think. Isn't it French for fish? Also? Okay, yeah. It's a fish equation. Y of u equals kind of gxy. We have the Helmholtz equation. And again, here I've this bit again. Let's see. This is x plus y here. There's an elliptic or elliptic ones. And I guess you've solved some of them in previous math courses. I have parabolic ones. U of t was kind of kappa x, uxx, also the diffusion equation. So for instance, heat diffusion, use this, or pressure. So I think in reservoir simulations you use this one. Well, it's simple. Anyway. And then my favorite is the hyperbolic ones. Here we find, for instance, the wave equation. T squared uxx one-dimensional wave equation. Also, you see, instead of using YY, I've used TT here. I mean, time is just a dimension similar to a space dimension. If it's T or it's Y or if it's X, yeah. I guess you know the difference between time and space. It's eating. So in the project, you will solve the 2D version of this. Okay, so 15 minutes break.